Okay. Okay, question before we start?
I mean, like that. You can't, you don't start in the five, you have to get there. And move it, move it. We can do it. No, it's literally just a. So the system rule in your working directory. Yeah, I downloaded so many.
Uh-oh, pay attention today because we're doing complex eigenvalues. Don't let the name don't let the name fool you. This just means these are two complex numbers. In principle, everything that we have done in linear algebra, we've done over the reals. Why is this? Because you're familiar with it. It's what we use in calculus. The important thing about reals is it's a field. Does anybody know what a field is? No, nothing outside of the grass on it. A field is a mathematical structure where you can add, subtract, multiply, and divide, as long as you're not dividing by zero. The rational numbers, a field. The real numbers, a field. The complex numbers, a field, right? You've seen it. How do you divide by a complex number? You can rationalize the denominator, right? That kind of thing. How many of y'all have seen this? So, in principle, everything we've done in linear algebra can be performed over any field, not just the real. We do the reals because it's got a lot of application, but you can do it over the rationals or any other field. You can do it over a finite field. How many of you are electrical engineers? How many of you have seen binary numbers, right? If you look at just 0 and 1 under where you have the rules 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, right? Let's like switch on, switch off. And multiplication is in the obvious way as well. This is an example of the field because you can add, multiply, subtract, and divide as long as you don't divide by 0. So when I talk about complex eigenvalues, why do I pay attention? Well, what we're now doing is sometimes we'll think about this over complex numbers from now. And this actually has some important applications back to the reals. The relationship between the reals and the complex numbers is important. And we're going to see when we're going to talk about complex eigenvalues, we're going to see a connection to real stuff. And the big thing the big thing about complex eigenvalues is when it's the root of a real polynomial, if you have a complex root of a polynomial with real coefficients, if you have a complex root that's not a real number, so it's actually got an imaginary part to it, what else do you know? What other root must you have? You have to have its complex conjugate, right? How many of you have heard this? If you have roots of real polynomials, they come in complex conjugate pairs, right? That's going to be important. This is actually important at one point in calculus. How many of you remember doing partial fraction decomposition? Right? You're still a little bit senior therapist about that a little bit, right? It's just awful, right? Why does partial fractions work? And the reason is if you have any real polynomial, it factors down into products of linears and irreducible quadratics, right? That's a big theorem. And so you'll have two different kinds in your partial fractions, one for the irreducible quadratics that have a pair of complex conjugate roots, and another form where you have just your real root. So without further ado, if you have and so if you have a matrix here, so if I give you an n by n matrix with real coefficient, if I compute its characteristic polynomial, what degree will that characteristic polynomial have? N, right? So if I compute this characteristic polynomial, it'll be a degree of the same size as the height of the matrix or the width, same thing, right? So if p of x has an eigenvalue, a plus bi, and here a and b are real numbers, then it also must have eigenvalue what? Right, because you have to have roots in complex conjugate pairs. Notice this statement that I've written is also true if b is 0, but it's stupid, right? Because if b equals 0, then what this says, if it has eigenvalue a, then it has eigenvalue a, right? Which is kind of a waste of time. But the interesting case is when b is not 0, because you have to have complex conjugates. Notice it is very important that the polynomial have real coefficients here. If it has complex conjugate, if it has complex coefficients, it doesn't necessarily have to have roots in conjugate pairs, only if it's got real ones. So what we can actually do because of this fact here, that the eigenvalues that are not real have to be conjugate pairs, is we can glean some interesting stuff about linear transformations out of this. And of course, every real polynomial, just like we said in partial fractions, factors into a product of linears and irreducible quadratics. There is no 3-degree polynomial that is irreducible real coefficient, right? Because a 3-degree polynomial has to cross the x-axis at least once. So it's got at least one real root, so you can always break it down. But this property here is going to help us glean some interesting stuff out of matrices. And in fact, in particular, at the end of this, we'll show basically how you can decompose 2x2 matrices. And since everything can be broken down into pieces of that, it's an important building block for the general case. So let me start off with an example. And so this is my first naive example. And in my naive example, I am just going to, let me compute some eigenvalues and eigenvectors. Let's let A be 1 over radical 2 minus 1 over radical 2, 1 over radical 2, 1 over radical 2. By the way, anybody know what this matrix does?
That's the angle.
It does. It rotates the plane by a certain angle, 45 degrees. So you might see if you can figure that out. Well, let's find that characteristic polynomial. Let's look at the determinant of 1 over radical 2 minus x, 1 over radical 2, 1 over radical 2, 1 over radical 2 minus x. Let's see if old Jim can still do a determinant. This is x squared. This is 1 over minus 1 over radical 2 minus 1 over 2 of those is minus radical 2x. And then we'll have 1/2 plus 1/2 plus 1. So there is my characteristic polynomial. Now I've got to see if I can figure out some eigenvalues for this. So this looks like a job for the quadratic formula. So see, that's going to be radical 2 plus or minus the square root of radical 2 squared minus 4. All right, agree with that? Let me clean this mess up a little bit. It's radical 2 plus or minus radical negative 2 over 2. And I can write this plus or minus I radical 2. So I get 1 over radical 2 plus or minus I times 1 over radical 2. There's my 2 eigenvalues. Notice, as predicted, what did I get? I got a pair of complex conjugates. Right? I don't want to dig deeper on this one. Yeah, so let's do this. Let me find the eigenvector for one of them. Then I'm gonna do another example where I go in depth. I'm gonna come back to that example quite a bit. Let's take a pause. Okay, so what do I do to find the eigenvector? This is a null space thing. And so all I have to do is compute a null space. The only obnoxious part of this really is the fact that instead of all having real numbers, I might have some complex numbers sprinkled in. But in principle, it's no different because you can add, divide, multiply by complex numbers. So let's see what we get. We're looking for the null space. I'm gonna subtract this sucker off the diagonal elements of my original matrix. So I'm gonna get 1 over radical 2 minus this mess. We'll have minus 1 over radical 2, 1 over radical 2. And I'm gonna subtract lambda off of this mess. I should get the same thing. This looks yucky. But it's actually not so bad. The first thing is it clear to you all that I can get rid, I can take this out by multiplying this by negative I and adding up here, right? So I'm gonna multiply this row by negative I and add it up. No, I'm not, by positive I and add it up here. But, so I'm gonna have 1 over radical 2 minus I over radical 2. When I multiply this by I and add up here, I get 0. Right? What happens when I multiply this one by I? What happens when I multiply minus I, that's 1 over radical 2, times I? That's right. I times negative I is positive 1. So this turns to 1 over radical 2, which is a big fat 0. And you know, I'm not shocked here that I get a row of zeros because it's supposed to be like a null space, right? Notice I can recalibrate this to 1 by multiplying this by radical 2. And so what I get is, this is equivalent to 1 minus I, 0, 0. Right. And so if I were to get an eigenvector out of this, well, think of it this way. This is not a real number, but who cares, right? I've got x1 is basic, x2 is free, and so I get x1 minus I, x2 is 0. So I get x1 is I, x2. So I get, for this one, okay, let's do one that's a little bit more, and I'll go through and I'll do both the eigenvectors, and I'm going to collect all this because I'm going to use this example later. So this is one that I just kind of made up at random because I knew that it was going to give me a characteristic polynomial where I had non-real roots. And what did I make? 1 minus 2. Same instruction. This one. Let's go through and let's find the eigenvalues. So the first thing I want to do is look at the determinant of 1 minus x minus 2, 3, 3 minus x. And this gives me x squared minus 4x plus 3 and 6 is 9. Now this gives me so what are my eigenvalues here? Well, set this sucker equal to 0, use the quadratic formula, and I get 4 plus or minus the square root of middle term squared minus 4 of 1 times 9, all over 2. And this is 4 plus or minus radical negative 20 over 2. And this turns out to be 2 plus or minus I radical 5. And once again, I get a pair of complex conjugate eigenvalues. By the way, you can always tell if you've got the eigenvalues right. Once you try to compute the eigenvectors, you have to get a row of zeros somewhere. If you come up with some eigenvalue and you put it in there and you muck around with your matrix a little bit, if you get a matrix that's still invertible, then you've messed up the eigenvalue somewhere. So let's try to find the eigenvectors for this. And I'll tell you something practical about this. It's sort of a shortcut as we go along. Let's do this one first. So what we're looking at is the null space. Let's subtract this off the diagonal. So I'm going to have what? Negative 1 minus I radical 5. Minus 2, 3, and 1 minus I radical negative 5. Now, again, this might look like a mess. In fact, it is a bit of a mess, right? But if we've done this right, there should be a row of zeros. Let me do the computation here. You know, I like putting real numbers in the denominator more than putting complex numbers, but I can set through it. Let's multiply this by, I'm going to use this to take this out. So let's multiply this. What do I need to take this out? Right. See my evil scheme, right? This is designed to just take this out. Right. So what do I get? Well, that's a 0. And of course, this row should be the same because I used it. There. Now, what happens when well, let me take this way. This should be minus 2 plus question mark, right? Everybody agree with that? So I'm adding this, and my question mark should equal 1 minus I radical 5 times 1 plus I radical 5 over 3. Everybody okay with that? Everybody see what I'm doing? Now let's test our complex multiplication here. Big fat denominator of 3. What goes in the top? We got to multiply this out, right? But these are complex conjugates, so it should turn out to be a real number. 1 times 1, 1. Then I have I radical 5 minus I radical 5. Look how lucky I am, right? And then the last term, I get minus I squared times radical 5 squared. Everybody agree with that? And what does this thing right here turn out to be? This is 1 minus 5 over 3. So this is minus 2 plus 2, and I have a row of zeros. So this should actually be and I'll take one more step here. Everybody okay with that? So my eigenvector should be, here what we have is x1 plus this mess. X2. So x1 is equal to minus 1/3 plus I radical 5 over 3 times x2. So for the first one here, let me kind of record this. I'm going to use this board here to record it. Characteristic polynomial was x squared minus 4x plus 9. Lambda equals 2 plus I radical 5. It's eigenvector. Let's see, 1 minus 1/3 plus I radical 5 over 3. Everybody okay with that? Let's see what happens when we compute the other one. Everybody okay so far with what we got? Okay, let's look now at the other eigenvalue. Let's look at this conjugate, see what happens. Now what happens? Well, now we're looking for the null space of the matrix. Well, now it's going to be -1 plus I radical 5 minus 2, 3, and now it's going to be 1 minus. No, I'm sorry, 1 plus. So it's just like the previous one, only somebody conjugated it. So what happens when we go through this? If we've done this right, we do the same thing. This should turn into a row of zeros, shouldn't it? Right, so I'm trusting that I haven't messed up any of my computations so far, but this should turn into a row of zeros. So this should be 3, 1 plus I radical 5, or 1 and 1/3 plus I radical 5 over 3, 0, 0. And so this time I get eigenvector, it's easy to check. Minus 1/3 minus I radical 5 over 3, 1. So with this, I get the eigenvector minus 1/3 minus I. radical 5 over 3. Notice the relationship between the eigenvalues and the vectors. I'm going to use this example later. Okay. Any questions? Okay, so let me use some terminology, some language that you're going to need. If you have a vector in Cn, you can break this up into real and imaginary parts. Let me call it something. A1 plus I B1, A2 plus I B2, AN plus I BN.
Question,
Yes,
is that a special C notation? Or?
yeah, so these complex numbers.
Okay. And
But
these are
this is a vector. This is a vector that's in high that has complex numbers.
Okay. So it's a C with a line in the middle like that?
Yeah. This can be broken up into, we'll call this V. Into real and imaginary parts. And I hate the terminology imaginary because these numbers really do exist. Just that's what they call it in call. But you can break this up into real and imaginary parts this way. You could certainly write this as right. So you can break it up into a real vector plus I times a real vector. Right? And this is sometimes called the real part of B and the imaginary part of B. So for example, if I give you this, if it's B, then the real part of B, you just go through, I mean, it's just like you're picking strawberries or something, just pick out the real parts. 2, 7, radical 2, 0, 3. Right. And the imaginary part for this particular example will be 3, 0, 0, 12, 2. Let's see how it is. Notice so this is one of the interesting things about this is is that you can actually break up any vector in Cn into a real part and an imaginary part. And both the real and the imaginary part are vectors that are real vectors. So later. Let me also make another observation. If V is equal to real V plus I times MV, then the complex constant of V Anybody seen this notation before? Anybody want to guess what the complex conjugate of this is?
Minus.
Yeah, that's right. So the notation bar. X bar is complex conjugate. And that basically means change the sign of every imaginary part you find. So for example, if I have a complex number, 1 plus I, its complex conjugate will be 1 minus I. If I have a stack of vectors, if I have this vector here, the complex conjugate of this vector is 2 minus 3I, 7 radical 2 minus 12I, 3 minus 2I. Right? I can also take the complex conjugate of a matrix by going through and taking the complex conjugate of any of all the elements in the matrix, right? So when I say complex conjugate of the matrix, I mean take the complex conjugate of everything in there. Let me ask you this. What happens if I take the complex conjugate of a matrix and that matrix has all real numbers as its entry?
Doesn't change.
It doesn't change anything, does it? Right? Because the complex conjugate of a real number is just that same number, right? Because it's got 0 imaginary part. So with this observation, let me point this out. If you have suppose A is a real matrix, then the complex conjugate of A is A itself. Do I agree with that? Now suppose lambda B is eigenvector. And again, let me stress to you the importance of the fact that this is a real matrix. If they have some entries that are not real, this doesn't work anymore, so you gotta be careful about that. Let's suppose we do this. And let's suppose that that my social life is such a level that I just want to sit around and conjugate this. And that's what I'm going to do. Let's take the complex conjugate of both sides of this, right? We've got a vector here. We've got a vector here. So let's do that. I want to use some properties of complex conjugation that will be easy to verify even if I guess this is true. This is the complex conjugate of A times the complex conjugate of B. And this is the complex conjugate of the number lambda complex conjugate of B. Everybody okay with that? The fact that this statement is true is easy to verify. And what's the complex conjugate of A? Well, it's A itself. It's real matrix. And there are those voices again. And it's this equation is speaking to me. It's telling me something. Hopefully something harmless. Actually, it's telling me something useful. What is that? It's telling me I could have saved the step on that first example I did for you. Does anybody see why? We started with AB equals lambda B, and we went through some shenanigans, and we came up with this. What is that saying to you? Yes.
That if you have a eigenvalue, then its complex conjugate will be the eigenvectors of that eigenvalue. I'm doing a very bad job. Basically, it's over there, right? So if you have an eigenvalue that is a complex number, then if you take the conjugate of that complex number, its eigenvector will be the complex conjugate of the other one by.
That's exactly right. Suppose you have an eigenvector pair. Then what is true is if lambda is an eigenvalue, so is, because this is also an eigenvector pair for A, so is lambda bar. And not only that, if lambda and V are a pair, then lambda bar and V bar have to be a pair, right? Notice that if V and lambda are real numbers, this tells you nothing, right? Because if V is a real vector and lambda is a real number, then this is just, you just get this equation back. And what it does tell you is if you get something that's interesting, like a non-real complex, then here is the eigenvector that we did here. We did another step, but that little computation right there says, I really didn't need to do this, because once I know that this is one of the eigenvalues, and this is its eigenvector, I could have just written this down, right? Which is kind of cool, right? I mean, that's useful. It saves you at least some work. Okay, any questions? Okay, so I'm going to finish this off with basically a way that you can decompose any linear transformation into space into basically a rotation. If it's got complex eigenvalues, not real, into a rotation and a scaling, right? So this is kind of interesting. And even though it's only for two space, this is the building block of what you need for larger dimensional space as well. So again, I'm gonna appeal to this example a little bit as I go along. But here's kind of the background page. So suppose I have a matrix of this form. So I'm going to call this important example. Suppose that we have and this is really most interesting when B is not zero. By the way, is this familiar to anybody? You all have seen stuff like this before. Y'all remember from some discussions we had this matrix here? Y'all remember this coming up on all quizzes, things like this. This, notice that this is a special case of this, right? If I take A to be cosine and B to be sine, here it is. There's going to be a connection with this, right? So we can forget about this for now, because it actually is going to show up in a moment. Now, if I were to compute the eigenvalues, yes, characteristic polynomial, we burn the retinas out of my eyes here. Wow. I get x squared minus 2ax plus a squared plus b squared. There's your characteristic polynomial for this. Now, you guys want to do the quadratic formula on this? Oh, you're going to like the outcome of quadratic formula. In fact, if you think about what an eigenvalue is, you might be able to figure out what you come out of there. 2a plus or minus the square root of 4a squared, squaring that, minus 4a squared minus 4b squared. How about that? Because this is a bloodbath here. Leaving me with b squared times -4. So this is 2a plus or minus 2bi over 2. So I get a plus or minus. How about that? This matrix is very easy to pick out the eigenvalues. And for the most part, I'm going to assume B is not zero. Notice if B is not zero, then you actually have honest to goodness non-real complex. If B equals zero, this is just a scalar matrix, right? If e equals 0, this is just a 0, 0, a. It's multiplication by a. So let's figure out. Actually, I'm going to take the negative one first. Let's figure out what the eigenvectors are here. And right. So now what I'm going to do here is I'm going to measure this. Okay. How many of you have ever seen this complex number where you graph the x coordinate along real axis and the y coordinate along imaginary? This is just like doing geometry, really. If I have a plus bi, and I represent it here, that would be going over a, so this is like a, and up b. Now forget about the fact that there's an I here. I think we can all agree this is a right triangle, right? What's the length of this right triangle? I agree. The old-fashioned Pythagoras theorem, right? And so let me point out that we can decompose M as follows. Where, what do I mean by R? R is a square. Let me try to convince you of this. What happens when I multiply this matrix here? This matrix actually turns out to be R cosine theta everybody agree with that? If I just multiply these two matrices, and I claim that these are the same, and all you got to do is look at the triangle, right? What happens when you take R times sine of theta? You get B. Everybody agree? Because B over R is the sine of theta, right? And so there, that accounts for these two right here. It should be a B and a negative B. Right? What happens? What is A? Well, A over R is cosine theta, so A is R cosine theta. So this matrix is equal to this matrix. Agreed? What's the significance of this? This means that if you have any matrix of this form, if you just happen to encounter this on the street, you can break it down into this times this, right? And what is this? This is a rotation. In fact, it should be theta radians counterclockwise, right? And this is a scaling. So I can describe this linear transformation that this does. What does it do? First, it spins it, whatever the appropriate angle is. And that angle actually should be just take B over A and take the inverse tangent of that. And it should spin it first, doing the cosines and sines, and then it multiplies it by R. So it stretches it or contracts it or whatever. So any matrix that you see like this, you can decompose this way. Everybody okay so far? So, and of course, what happened, this even works with B equals 0 because all your, instead of, you don't rotate at all, you just stretch. That's it. So why do we care about this? Well, let's go back to, because I mean, how often are you going to encounter this matrix, right? I mean, this is all cool and everything, but how often Are you going to see something like this? And the answer is not often, but almost a lot of things are going to be similar to it, right? So let me work this example here that we have. Put the right here. Let's take I call this minus 1, 2, 3, 3. Let's take lambda. I want to take the minus eigenvalue. So 2 minus I right. Let's take the eigenvector. Minus 1 plus I radical 5. Oh, okay. Oh, it should be a plus, isn't it? Yeah, this should be. 2 minus has. Okay, so we've got that eigenvector. Notice I've rescaled this. It's basically this one times 3, right? That's all right. That makes it easier. So let's let P equal real V in P in this case. So I get see the real V is minus 1, 3, and the imaginary is minus radical 5. So what's the inverse of this? Well, this is a 2 by 2, so I can figure this out. It should be 0 minus 1. Chances I don't know these. 1 over 3. 5. I've got this a little bit off, so that should be minus. Oh, that's I'm mixing that here. Hold on just 1 second here. This is 0, 0, 1, 3, 1 over radical 5, and 1 over 3 radical 5. So correct this. That's going to be so that this should be well, actually, I'm gonna do what I've got written down here as I work. So let me work off the other eigenvector, which is this one here. So if I take that eigenvector and I look, P is the real part of V and the imaginary part of V, then this is minus 1 over 3 radical 5 is 0. And P inverse is equal to 0, 1/3, 1 over radical 5, 1 over 3 radical 5. And a quick check of this, that's 1, 0, 0, 1. Good. So if I look at M equals P inverse one minus 2, 3, 3 times P. So you can do this computation out. Make sure you do this computation out. I actually got 2 radical 5 minus radical 5. Notice this is exactly that form that we have. A minus B, B, A, like that. And so in particular, minus 1, 2, 3, 3 should be P times this matrix here. So in other words, if I have a matrix that has complex eigenvalues, then it is similar to a matrix that is just a rotation and then a scaling. So here is the theorem that encapsulates this. And so you should check this out because this kind of problem is kind of cool. Let A be a 2x2 matrix with complex eigenvalue, complex eigenvalue A minus BI with B not 0 and eigenvector so take A minus BI, eigenvector B, and then A can be written in the form PM P inverse with P equal to the real part of B and the imaginary part of B. So you got the columns from here and M equal A minus B, B, A. So what this says is if you have something that has a complex non-real eigenvalue, then it may not be of this form, but it's similar to a matrix of this form. So with respect to some basis, you can break it apart into a rotation and scale. Any questions on it? Okay, well, I will see you folks on Friday.